can get this started.
Well, thanks, Greg, for having me here. I've been promising to come here almost a year. And now, when I'm on a parental leave, I finally found time to do that. So the title of my talk is Plasma in Extreme Environments for National Security. So although I come from the physics field, I spent most of my life in aerospace and mechanical engineering departments. So I decided not to deep dive in one particular problem, but rather to give an overview of 4 different problems I will talk briefly about. And just to give you a rather broad perspective, not complete by any means, what plasma in aerospace engineering means for us. So before I start, okay, okay. So Center for National Security Initiatives is fairly young. I think we are 4 years old. We are actively hiring in 5 different fields, plus minus. So we have some room and some additional vision to that. Hypersonics, RF engineering, cybersecurity, space domain awareness, and our youngest direction is probably in autonomous systems. So we were formed with the vision that CU Boulder would like to increase participation in DoD research and DoD activities, and that reflects the fact that Department of Defense presents a single-digit percentage in funding on a CU Boulder landscape compared to NASA, which is probably the majority of the funding that comes in here. So our focus actually to work on the problems that are interesting to Department of Defense and is of interest to us. So this is our structure. Ian Boyd is a faculty at Aerospace Engineering, is our director. We have 6 dedicated NSI researchers from different fields. We have a number of campus collaborators. Most of them are engineering, so computer science, electrical engineering, mechanical engineering, aerospace engineering, and few in other fields. We have our own research operation team who helps us with writing proposals. Some of these people work also for the RIO, Research Innovation Office. And that's how we look, and we keep hiring, especially in this dedicated NSI researchers column. So without further ado, this is the problems I'd like to chat about. All these problems are related to very high speed flows and the physics that's going in these flows. And what happens when we would like to communicate with these type of flows? What happens when these flows hit the surface of a flying vehicle? So I will first talk about thermochemical and equilibrium and shock flows. And then each problem, second, third, and fourth, are sort of related to the first problem in one way or another. And that's why, we can stop at any problems and, call it a seminar, but I hope I will at least get through the first one. So the basics, how does the hypersonic flow, and hypersonic flow is a flow that goes, or you're going through that flow with Mach number, let's say, larger than 5. The strict definition of hypersonic flow is actually when you start seeing these physical processes that are highlighted with different colors. So you're looking at the diagram of altitude versus velocity of your vehicle. And if you sit in the vehicle, you're essentially talking about velocity of incoming flow. And you can see here that most of the trajectories of man-made vehicles that we are built are lying, well, unfortunately, outside of the ionization realm. But nevertheless, ionization, all these processes, such as vibrational excitation and dissociation processes, are the precursor to the formation of plasma that is showed on the right here. And one of the trajectories, since it's a velocity altitude map, one of the trajectories does cross the plasma formation, and that's a trajectory of a Stardust capsule. It's a NASA capsule, NASA program that actually captured the dust from the comet, from the tail of the comet, and then made a re-entry back to the Earth, and the record-breaking velocity of 11.5 kilometers per second. And it was a lot of ionization happening in the flow field of that Stardust capsule. But just to give you perspective, what kind of plasma I'll be talking about? It's a fairly cold plasma. Electron temperature is between 0.1 to 1 eV. It's ideal or close to ideal plasma, so it's a pretty low ionization degree, 1 to a few percent. And it's a thermally and chemically non-equilibrium plasma, meaning that the rate of establishing a thermal and chemical non-equilibrium in plasma is comparable to the residence time of the flow. Residence time of flow is the amount of time that takes flow to go from the undisturbed position to the wake of the flying vehicle.
And so you're showing processes that occur at a certain altitude just because an object is moving fast.
So, right. So when an object is moving fast, this is how the flow field around that object looks like, right? You're forming a shock because you're moving faster than the speed of sound. And depending on altitude, your shock will look different, right? We're talking about 40 to 80 kilometers altitude. At lower altitudes, you will have a sharp shock, basically like, less than a millimeter, probably less than that. And at the higher altitudes, you'll have a more diffusive pattern on the shock, shown at the bottom here. Just to give you perspective, what are the pressures and temperatures in the shock? Pressures ranging behind a fraction of atmosphere, a fraction of 1 bar. So it's a 1/100th of a bar if you're flying high, and up to atmosphere and probably higher when you're flying low. So even if you're flying on a 40 kilometers of altitude, because of shock compression, you have an atmospheric pressure behind the shock next to your vehicle. Okay, so it's a pretty dense flow, right, compared to, let's say, astrophysics or, like interstellar space.
How does that compare to the ambient pressure at 40 kilometers? Is that
so
10 times? Or?
So the ambient pressure is between 1 and 100 torrs. So you're like 10 to 100 times more than that. So that's a degree of compression for the shocks. It's probably more than closer to 10 than to 100. And the temperature, varies from 5 to 10K, 10,000 kelvins, and sometimes it goes higher if you're talking about superorbital velocity. You're coming back from the moon or Mars. What's interesting here is the composition of the flow. I won't be talking about particular species here. I just want to show how the composition changes. So you're looking at the composition and the function of distance along the streamline, and the streamlines are shown here by the wide curves along the trajectory, along the vehicle. And different color corresponds to different species. You have here atomic species such as N and O, and nitric oxide, and of course some molecular species. So the solid curves here describe an actual concentrations of how they change along the streamline. And the dots of the same color correspond to their equilibrium concentrations at that local temperature and pressure point. And you can see here that almost in all of the conditions here, your one color, dot of one color doesn't correspond to the curve of the same color, meaning that you're always to some degree of thermochemical non-equilibrium. You're always lagging behind your equilibrium concentrations. What's interesting here is that plasma species, NO+, which is a dark navy color here, appears only on the 40 kilometers of altitude, and it's not really present on the high altitudes because of the lack of collisions to form plasma species. So flow gets excited, but it doesn't get to the point of plasma species formation. It takes longer time because you have fewer collisions at higher altitudes. So you don't really form plasma at higher altitudes. So this is the basics of how the flow looks like. Now, plasma. When we do have plasma, if you're going low enough or you're flying fast enough, so what are the driving mechanisms for plasma formation? So this is a chart showing essentially an ionization distance as a fraction of, as a number of mean free paths, and depending on the shock speed, right? So what we're looking at, Apollo come back from the moon at 10 kilometers per second. Satellites are flying on the low Earth orbit, flying at 7.5 kilometers per second. So 7.5 is what you need to send satellites in a circular orbit. Just to give you perspective, DoD, Department of Defense, hypersonic vehicles probably won't be flying that fast. They will be flying slightly below orbital velocity. We don't really want them to leave atmosphere. They're pretty expensive. Okay, but what you're seeing is that the major driving reaction for plasma formation is called an associative ionization reaction, when you have collision of atomic species, NO, forming NO plus and free electrons. And that's why you need to vibrationally excite your flow, and that's why you need to actually dissociate your flow before you can get to that reaction, right? You have to have atomic species, and NO plus is the easiest, energetically easiest ion to form. And you go faster in velocity, it takes fewer and fewer mean free paths to excite your flow, right? So it takes 7 of them at this range and only a few of them when you fly in the orbital velocity. Then there is a jump because you activate another mechanism that removes NO plus from your flow by means of charge exchange reactions. So you start forming different ions like N2 plus and so on. And at very high velocities and superorbital velocities, you actually can form plasma with direct electron impact. So you hit the atomic species with electrons and you create avalanche ionization. You produce 2 electrons out of it. But that happens, at pretty high velocities. So just to give you perspective, what mechanism of plasma formation in hypersonic flows on the Earth we have in general.
So I don't want to divert you too much, so I could ask this later. But is it obvious what the advantages of, say, hypersonic flight at 40 kilometers compared to, achieving orbital velocity is?
Yeah. It's the lower you fly, it's harder to detect. And I have actually figures showing makes it obvious, but it's more stealthy. Let's be honest. I'm talking about national security applications. So flying low is, especially if it's a maneuverable flight, right? You maintain the maneuverability, you maintain communication. It's nicer than a ballistic missile that goes some kilometers in the atmosphere, right? And everybody can see it flying. So we've been past that point.
So is there a minimum altitude that you can think about hypersonic flight?
I would say 40 probably is getting close, because otherwise, the atmosphere is too dense and you're facing a very high heat fluxes. So I know 40, between 140. This is your envelope of the flight. Yes. So I promised to talk about modeling in my abstract. So this is how the model looks like, and there's some legacy background to it. Let's be honest. So the first people who actually looked into hypersonic flights in a civilian sense was NASA people. They flew Apollo and Gemini missions, and they flew space shuttle 100 times. So they recognized by flying those objects, that those vehicles, that at some point, they start comparing parameters they measured during those flights with their models, and those were equilibrium models, and they recognized that they're not matching some of the parameters of those flights. And at one point it got pretty close, so they almost lost the space shuttle because of the wrong prediction of trim angle of the moving surfaces. So in order to account for non-equilibrium that I just talked about, that non-equilibrium degree of species in the flow, they come up with what is called a 2-temperature model. I know in physics there are 2 temperature models where you consider temperature of electrons and heavy particles separately. So this is very similar. It's just we are looking not only on electron temperature, we are looking at vibrational temperature, so how our molecular species are excited. and we call it internal temperature. And I showed you that actual species concentration lagging behind the equilibrium values. So you can imagine that your rate of processes are slower than your equilibrium processes. And in order to account for that, people introduced a governing temperature, which is the square root of your heavy particle temperature and their internal temperature for vibrational degrees of freedom. And they analyzed a bunch of data on all sorts of levels. That's data from the 1960s and so on. They analyzed density ratio that was measured in shock tube facilities. They analyzed, shock experiments that contained electron concentration. They tried to predict that. They even analyzed excited species populations. And they essentially, managed to formulate coefficients for this rate of non-equilibrium chemical transformation, non-equilibrium dissociation, such that if you use the square root of two temperatures, you will be able to qualitatively predict the behavior of this thermal chemical non-equilibrium that you observe in flight experiments. And this was generalized. So this model, this is actually the core of two temperature model, the bread and butter for NASA people for almost 40 years, and they still continue to use it. So they come up with this model to describe a non-equilibrium dissociation for nitrogen, but also later on they generalized, this sort of concept to describe non-equilibrium reaction rates for ionization, for charge exchange, and for electron impact. So they essentially produce a set of parameters that specifies these C and N and the activation energy for this mechanism that are reproducing experimental data if you use them with a governing temperature that is square root of two temperatures. So the model was actually adjusted such a way that it explains experimental data. And when it didn't explain experimental data, it has been adjusted further. And by no means it's a physically strict model, right? If you don't have a thermal equilibrium in the flow, you can't really talk about temperature in the flow. But it worked very nicely for NASA. And 20 years ago, when hypersonic program received interest from Department of Defense, DoD has adopted this model for their own needs. And this is where this tiny wrinkle sits. This model was developed for NASA flows, which is much higher velocity, more rarefied than flows for DoD. And this is where we are now. We are trying to get away with this model and build more accurate models. And I will talk how more accurate models look like for Department of Defense. Just to give you a perspective, yes, we need to account for thermochemical non-equilibrium. It does sound like, an elusive concept, like, well, can we just, model an equilibrium flow or perfect gas and get away with that? Well, short answer, no, we can't. So if you take a 45-degree ramp and, 40-degree cone and place it in a shock tube facility, such as here, right? I'm not sure how audience is familiar with the conventional shock tube facilities that hypersonic people use, but essentially you have a high pressure chamber and then you have a diagram separating them and you have a low pressure chamber. And then you break this diagram in some way, sometimes mechanically, sometimes it ruptures itself because the incoming pressure is so high. So like, let's say you're talking about 100 atmospheres in one section of the shock tube, and you're talking about 10 to minus 5 torr in another section of shock tube. So when the diagram breaks, you have a shock forming going from left to right, and this is what's shown here. And then you have some sort of nozzle or just expansion type of test section that you can place your object in here. And there are some multiple variations how you do tests, but that's essentially how you create shocks on the ground on Earth. You
create an explosion.
Well, explosion is something. It's a chemical term, right? So people do create shocks using combustion and detonation. It's slightly different setup. But in theory, you don't really need to create an explosion. You just create a pressure difference. And pressure difference is already a shock by definition. So that's how it works. So it turns out if you measure the shock thickness for a 45-degree cone that is placed in your test section, and if you try to model that, the flow, look how the boundary layer and that on that cone looks like, how thick it is, right? Because your flow has to actually stop at the surface. It goes from supersonic velocity to 0 at that cone. If you try to predict the distance, the thickness of that transition from a supersonic to 0 velocity flow at the surface, you must include effects of multi-temperature model. You must include the fact that your flow is not in a full thermal and chemical non-equilibrium. You can assume perfect gas when there is no chemical reactions, and you can assume equilibrium gas when you recognize that, yeah, chemical reactions happen, but they happen instantaneously and they reach equilibrium right away. But none of these assumptions will actually give you a prediction of boundary layer thickness. And only if you actually, assume multi-temperature model like I described on the previous slide, you'll be able to actually somewhat have a good match of the shock layer thickness. And the further you go along the coordinate, the x coordinate of that cone, the more you need for this model, because the non-equilibrium effects become more and more pronounced. So hopefully I convinced you that two-temperature model did work nicely. It was cheap and expensive, very intuitive, and very popular back then. But time went by, and government spent more money, to do additional tests at conditions more relevant to DoD applications rather than NASA applications. And the evidence was piling up that two-temperature model was giving you a qualitative picture, but not quantity. So like this, description of heat flux and the pressure on a similar, these double cone experiments, when you have just a number of cones facing this shock, doesn't matter what kind of model you use, it's pretty hard to describe a newer experimental data. So 2T models doesn't always work for us, and this is why we wanted to move from them.
Just for the shock tunnel, how long is that flow maintained in one of these experiments?
Between 10 microseconds to 1 millisecond, depending on what kind of physics you want to capture. If you want to capture chemical reactions, you design shock tunnels, shock tubes with a microsecond duration because they happen faster. If you want to capture turbulence, this flow phenomenon, you want to go into millisecond regime. They take longer. Yeah. So this is actually, that was history, legacy, and this is where we are now. 10 years ago, when I just started my postdoc in Michigan, people sit down and said, okay, well, how we can do better than two-temperature model? How we can describe vibrational degrees of freedom? And when electron hits molecule, electron quickly thermalizes to vibrational temperature rather than to heavy particle temperature. So knowing better vibrational degrees of freedom directly translates to knowledge of electrons and their temperature better too. How do we describe vibrational degrees of freedom better? Can we get rid of the assumption that there is an internal temperature and see what's more accurate? So clearly, vibrational degrees of freedom are quantized. So oxygen has 30 states, vibrational states. Nitrogen has 50 or 60 vibrational states, and so on. What if we resolve each vibrational state individually? Just essentially come up with a conservation equation for each vibrational state of each air species. And we did that. So it took us 10 years. You can see conservation equation showing here. It's essentially dN over dt plus some transport terms giving you source terms. And source terms are essentially showing that these vibrational states can be destroyed in collisions with other vibrational states. It can get dissociated. It can get formed due to recombination when you form molecule. So the physics sits in these source terms, and you have to have state-specific reaction rates in order to make sense out of this equation. Otherwise, if you don't have reaction rates that are describe each state, you're not moving with a state-specific model anymore. So we applied trajectory methods. We essentially modeled how two oxygen molecules collide and what happens with them. And we ran billions of trajectories for that. And we essentially statistically analyzed the outcome of these reactions. So you're looking here at the exchange cessation type of reaction. And we essentially derived reaction rates for each combination of initial and final vibrational states of this reaction.
Are you actually modeling this with quantum mechanics?
This is the classical physics. Essentially, it's the second Newton law, because particles are heavy, and you don't really need to dive into quantum mechanics.
Okay, but you are doing individual particles and their
you're solving the four-body problem essentially here. Yeah. And you plug in all these reaction rates in the right-hand side of this equation that is above, and you solve it simultaneously, and you get this picture. So you're simulating. So the symbols here describe each state, and the line here assumes that there is equilibrium. There is an internal temperature. And you can see here that indeed all these states cannot be described with one single temperature. And you do really have an improvement by modeling these vibration states separately. It's a pretty expensive calculation compared to a simple two-temperature model, but it's still very tractable using modern computers. And just to give you an example, that shock tube facilities I talked about, they did measure a vibrational temperature of oxygen in the shock flows. And in 2015, that was done in Moscow State University. And 2021, it was done in a much better laser. You can see by the used uncertainty bars. Essentially your vibration exciting oxygen from 300 kelvins to a few thousand. And you can see that state result model that is shown here by black lines does get into uncertainty bars compared to a two-temperature model that is missing those uncertainty bars. So we do see improvement by treating individual states separately compared to two-temperature model. So that's the current state of the art, how you deal with vibration degrees of freedom in hypersonic flows. So I'm wrapping up my first, and this is the longest problem that I will be talking about. A couple of words where we're moving with this, right? So you might notice that I talked mostly about heavy particles and neutral particles. There was not much plasma to it, but if you want, we want to go faster and we want to go, lower in altitudes where plasma does form. So we would like to include electronically excited species in our flows, in our simulation, and we would like to include a plasma formation. That is the next logical step after you excite your flow. You have plasma formation. Treating electrons in the same way that we treated heavy particles won't be physically accurate. Electrons are lighter particles, much lighter, if particles at all. And people start, providing us data where they apply different quantum methods, like Greg mentioned, to describe collision of electron with, let's say, nitric oxide, and produce a state-resolved data of nitric oxide electronic excitation. That is a fairly fresh paper from 2022. So these are cross-sections for different vibrations, and you can see here that this data is far from being trivial. So it has some peaks and resonance and valleys, and all this data will be should be incorporated as the next step in our models of heavy particle airflows. When you collide, air species electrons, you have much higher chance of crossing the different potential energy surface. So essentially, you can't really run particles on one potential energy surface, assuming that forces between particles never change. You have to deal with several potential energy surfaces, and that's actually pretty, hard thing to do. We have to jump between different trajectories, following different energy curves that is shown here. And this happens much more often when you have electron particles rather than heavy particles. So this is actually where community is moving toward, learning how to, jump between potential surfaces and how to use quantum mechanical methods. It is not brand new methods. Physics department, did develop them actually in the 60s. But you can imagine the barrier we have between aerospace engineering and physics. It always takes an enormous effort to accommodate, methods from one field into another. So we're getting there. Another direction is, well, what happens with the flow when it hits the surface, right? Before that, I was just talking about the gas phase and never bother myself with the surface. Well, it turns out that when you hit the surface with such a chemically and thermally active flow, surface does respond, and respond in a pretty non-trivial way. So one of the great examples I like to talk about is when you hit the phenomena called shuttle glow. When you shuttle surface, space shuttle surface, that actually coming back from from the orbit is exposed to dissociated and flow containing oxygen, nitrogen, and nitric oxide. And you see this formation of this red-orange glow at the tail of the space shuttle. It's a fairly harmless effect. It doesn't really change the surface margins for the space shuttle, thank God. But if you're talking about national security, you really want to have a good understanding what's glowing, how much, and at what wavelengths, because otherwise you're giving yourself, you're just exposing yourself too much. So from the physics perspective, it's a pretty interesting mechanism. You have oxygen atoms absorbed on the surface, and then you hit them with other radicals, such as oxygen atoms or nitric oxide, and the surface helps you to recombine back into molecular state. And that molecular state is excited, it's electronically excited, and after some time, it emits photons, deactivates, and these photons have red and orange glow. And this was just funded by FSR, and we're gonna try to model this effect for silica surface, for silica protective surface. That's actually pretty interesting physics. So I'm done with the first problem. I probably will be able to cover 2 or 2.5 of them. Greg, do you want me to answer questions now, or jump into a second problem?
I think if anyone has any questions, you should go ahead and ask them. But otherwise, we can
do it. We can do it at the end, yeah, if it's not critical for understanding. So second problem is more plasma related, right? So now we are flying on a hypersonic speed. We have plasma forming. Okay, good. What's next? Well, we want to talk the vehicle. We want to communicate with with the devices on board, or we want to communicate with the pilot on board. So you can see that if you're talking, like Greg mentioned, right? So you're launching an object from the left, and it's either a ballistic missile that can go 1,000 kilometers altitude, and if you're sitting at the target space, you can actually easily track, right? When it's up high, you can easily spot that missile, before it actually reaches the maximum altitude. But when you're flying low, when you're staying in atmosphere like this, if you're either a boost glide vehicle, the vehicle with the booster attached to it, or if you're actually flying on your own and carrying a fuel supply, which is called an air-breathing vehicle, you're staying low, and it's harder for the target to spot you, because it's essentially like happens only at the end of the trajectory. The problem with these trajectories, with the low-lying trajectories, that most part, if not all of the trajectory, is lying in an atmosphere, and hence you're going to have plasma to yourself around the vehicle for the entire trajectory, right? So when you're high, there is no species to form plasma. When you're low, you're surrounded by plasma all the way from the beginning to the end. And if you're using a gigahertz frequency, and that's a normal frequency for communication, you're gonna see problems communicating through, because plasma density turns out to be right at the communication frequency. Plasma frequency turns out to be right at the border of communication frequency. So, you can recall the movie with Tom Hanks, Apollo 13, when they're coming back from the moon and everybody waits and there's a suspension going on. So this is the communication blackout I'm talking about. When your RF waves cannot penetrate through plasma layer and reach the receiver at the on board of the vehicle. Beautiful experiments were conducted to capture that. In 1980s, seven blunt bodies have flown, and that's the program called Radio Attenuation Measurement Experiments, RAM experiments, whether they measured number density of electrons using reflectometers and Langmuir probe at the end of the vehicle in these flights. And some of the vehicles actually inserted water in the flow field in the hope of reducing plasma number density, so reducing electron concentration, so the radio frequency waves can penetrate through plasma layer. So by now you should know how temperatures look like for this type of flow fields. It's between 10 and 20,000 kelvins. It's a pretty high temperature. Associative ionization reaction N+O produces the majority of electrons for these type of flow fields. And number density of electrons is pretty low. It's between 10 to 12 to 10 to 10 electrons per cubic centimeter. So it's a fairly non-dense plasma compared to, let's say, fusion plasmas. If you want to model these experiments, there is a wide variation of reaction rate data that you will end up using. Just so take a look at this reaction. You have atomic nitrogen and atomic oxygen colliding and producing NO plus and electron minus. You have to use you have to use this reaction and to model this reaction at tenths of thousand of Kelvin, right? Because heavy particles, their temperature will drive this reaction rate. Okay. Ground facilities cannot reproduce such high temperatures. 10,000 maybe, but even then you will have problems measuring that reaction rate. But 20,000, I never heard of such facilities. So you ended up just guessing that reaction rate. And by guessing, you introduce a pretty wild variation of electron number density in your flow field. So that's a challenge. It is an unsolved challenge. So we are not competent enough to actually produce a more accurate reaction rate. Uncertainty here is more than one order of magnitude. So Aerospace Department and the people at NSI recently won Office of Naval Research URI grant, which is a 5-year grant to actually look into and model through experiments and through quantum kinetics, quantum chemistry, to model reaction rates for this associative ionization, and with the hope of producing more accurate rates, not only for NNO in a ground state, but for nitrogen in an electronically excited state, which is actually a lot more reactive, as you can see by, a lot more reactive in producing plasma, as you can see by green line, compared to nitrogen and oxygen in the ground states. So, you might discover a different repeating mechanisms in plasma formation for airflows. Just to give you perspective that we are working on this problem in the other side of the campus. Okay, now you've got plasma, you kind of modeling somehow. You want to mitigate that blackout. Like, what do you do? Well, in 2006, there was a DoD workshop where people, probably 20-25 people got together, and they just listed possible mitigation strategies, and then they voted for these strategies. And all the experts were present there except optical experts, optical communication experts were there. And they actually voted, and you can see here number of votes given for a particular strategy as a number number in a bold font. And part of the circle represents the viability, the number of votes for the particular mitigation strategy. So the largest circles here got 13 votes, and they proposed an electrophilic liquid injection from the surface of the vehicle, such as water, which that experiment did back in the 80s, or either building a heat shield of the vehicle. So by ablating, by destroying that heat shield, you introduce species that also possess electrophilic properties. So they essentially attract electrons to themselves and reduce number density of electrons in the flow field. So it's roughly the same techniques, but to some degree. And then there is a trajectory shaping technique, and magnetic control is also a pretty cool technique. And there are some very intrusive techniques such as air spike, that actually spike that protrudes through the hypersonic flow, and it received a negative amount of votes because people already did that and showed that it's very hard to get your air spike keep from burning to the base. So people in Ian Boyd's group tried to describe these experiments that injected water in the flow field. So you can inject not only water, you can inject different oxides, and that's why a heat shield ablation also works. You introduce oxides in the flow field. You can introduce peroxide and different gases they also have some pretty negative electron affinity to themselves. But water is nice because it's environmentally friendly and it's simple. So that's why experiments use water in the first place. So I don't want you to bother with exact findings of these studies, but one of the outcomes of these studies was that efficiency of electrophilic injection in the flow field really depends on the phase of your electrophilic substance. If you inject a liquid droplets, such as was done in an experiment, right? So let's think what happens with the liquid when you inject in the flow field. If you have a very low pressure, all right, in a very high altitude, and you put a droplet in it, you will have a flash atomization, right? Your droplet, large droplet, cannot sustain such a low pressure and breaks down into smaller droplets. If you have a high pressure, high aerodynamic pressure, your droplet will also atomize, but by means of aerodynamic forces, which is also interesting how that happens. But either way, you're going to see atomization of your liquid, and then these micro-sized droplets will attract electrons to themselves to the point where they become negatively charged. They will form a space charge sheath around them, and they will get charged to the floating potential, and they will behave like a Langmuir probes essentially. And you can imagine that at some point they will stop being effective because electrons will stop flocking to them, and those droplets will just attract positive ions. But if you inject water in a gas phase, right? So essentially vapor, right? Not liquids, but vapor. Simulations show that the major mechanism of electron removal is based on chemical reactions. One of them, so once you introduce water vapor in the flow field, the water vapor breaks down into radicals such as atomic hydrogen and OH. And then there is a pretty quick reaction such as N plus OH, giving you another molecule and O, and giving you a hydrogen radical. So this reaction is pretty fast, and it's pretty fast in the sense of removing atomic nitrogen from the flow. And you can recall that associative ionization degree reaction, O plus N, is a driving mechanism of the plasma formation in the first place. So it works out pretty nicely if you remove atomic nitrogen and sort of slow down associative ionization mechanism in the flow field. So that was an interesting finding, in my opinion, that by changing the phase of your electrophilic substance, you change the blackout melioration mechanism. And simulations show that the vapor injection, which is shown by dashed lines here, are slightly more effective than experimental data that reflects liquid injection, compared to no injection at all, which are shown by square symbols, which is a pretty interesting finding here. I'm not sure if somebody tried to model an actual droplet injection in a hypersonic flow field. Probably they did, but I imagine the breakdown of the droplets is probably a pretty complex mechanism for this type of flows. Okay, so I have 10 minutes to the end. I had 2 more problems to go, but I don't think I will do that. I'll just mention what they are and show a couple of cool videos. If Greg, is it fine if I do that?
Yeah.
Okay.
Great.
So a pretty crazy technique, in my opinion, related to the surface problems is how to cool the surface. And you know the space shuttle and the flu, they were cooling by essentially shedding the surface away. It's called ablation. For DoD vehicles, we would like to avoid that because changing shape is never a good idea. We want to maintain aerodynamic characteristics for our flow.
How much ablation are we talking about here?
So much
you
that
say enough to change the shape. I would have expected,
we're talking about millimeters, but millimeters are enough to change the flow from laminar to turbulent, and turbulent flows have 3 to 4 times heating rates more than laminar flow. So by triggering this transition from smooth flow to turbulence, due to this millimeter ablation, you can change everything. And if that portion is not covered with enough of TPS protection, thermal protection, you may lose the vehicle. So that's pretty crucial. So if you don't want to ablate radiation, essentially your only mechanism, right? So sigma T24, your Stefan Boltzmann law, is the only mechanism you can cool your surface, unless your surface, when it's heated, it emits electrons, right? And that happens with metals, right? It's called thermionic emission. So electrons essentially in a hot surface, they vibrate, they move around, and some of them, the tail of distribution, can leave the surface. And when they leave the surface, they carry away energy and provide additional means of cooling. So without changing the surface shape, you can get rid of electrons, transfer them from the tip of the surface somewhere where the cooling is not as critical, and essentially make a circuit of electrons and provide cooling to your leading surface. It's a pretty old technique in the sense that it's a power generation technique that was investigated in the 60s, but for cooling of hypersonic flow fields, it was never investigated. And I would like to show how the discharge, essentially talking about the discharge that electrons create, how the discharge look like in the Texas A&M lab that we managed to achieve. So essentially you heat the surface, the tungsten surface with the laser, surface becomes hot, starts to emit electron, and if you apply a little bit of voltage in between the cathode and anode, you can actually create a sustained ignited discharge in between these two. And
so is this just a discharge in vacuum?
It's a 1 torr argon pressure. So it's essentially it's a vacuum, and this is actually what the culprit lies, how it's going to behave in high pressures. I assume that it will be different. But so far we just played with 1 torr of argon pressure, and that glow, as you see here, is due to excited argon photons. And by doing so, they measured the temperature with a pyrometer, and they did observe a drop in temperature of the surface when the discharge becomes ignited, which is also a pretty cool observation, in my opinion. And we did try to model that, and people did try to model that too. So, with different degree of success. And the last problem is about flow modification with plasma. Have no time just to mention that plasma can modify the aerodynamics of the flow. As you can see here, we can actually delay the transition to turbulence using different plasma discharges. And plasma can reduce the drag on the vehicle if it is ignited in the right place. And also plasma can enhance combustion inside the vehicle by creating additional radicals that are more reactive than your standard combustion mechanism sees. Flow spans milliseconds within the combustion chamber of hypersonic vehicle. So the faster you ignite the fuel, the better thrust you get during the hypersonic flight. This is and people did simulation of how the kinetics changes during different discharges, and I can refer to this later on. But this was done in Princeton. This was done in Princeton and in my alma mater back in Moscow. That was a pretty exciting research overall. So my conclusions. So plasma physics and aerospace engineering are two intertwined research fields, and we cannot really exist without each other. Well, I guess you guys can, but we can for sure. Sometimes we want to have plasma in the flow, and sometimes we don't want to have plasma in the flow. Plasma physics needs to be considered, at least for us, as a part of the bigger challenge, the bigger problem. Plasma experiments in ground facilities, at least for us, is quite different for aerospace environments. That small video I showed you is a good illustration. One torr, you can ignite the discharge, but what happens when you have a crazy hurricane flow flowing around your vehicle? Can you really ignite the discharge? I have my doubts. Plasma models in aerospace engineering can have different fidelity, scalability, and application envelope. So we need to work in addressing that. Thanks for attention, and I'm ready for questions.
Thank you. Yeah, so the floor is open for questions. If you have questions online, feel free to speak up or write them in the chat.
Yes, I'm sure someone's thought of it, but it looked like the plasma density was decreased as the back of the vehicle. So what if you had a window out the back that communicated with some intermediate satellite or something? Would that be a way to get around blackout?
That's a possibility for sure. Unfortunately, we would like to place communication devices toward the beginning of the vehicle because of the mass limitations. Otherwise, you have to create a whole bunch of additional infrastructure to the vehicle. But that's possibility, but also a possibility to create more slender vehicles, more sharper vehicles that create less plasma, that can just essentially pierce through the flow with much less disturbance. So that's a possibility too, yeah.
So you rely a lot on estimating collisions and reaction rates. I'm curious whether you think that the most important contribution to modeling comes from experimental measurements of reaction rates or theoretical modeling. Doing collisions of oxygen and nitrogen and so forth.
The most important contribution comes from flight experiments that are incredibly expensive, and it's one of the lifetime achievement. During your career, you can allocate money for one flight experiment. So they're extremely valuable, especially if it's a failed flight experiment, in a sense that like people saying, right, one failed fails more than 10 launches. So flight experiments is very important. I don't think I want to be gentle about it, but conventional shock facilities, with the conventional laser diagnostics that we have now, maybe within their limits already. If you go to femtosecond lasers, when we have very short pulse lasers, or like attosecond lasers, when they can deliver amounts of energy very quickly we can probably track individual chemical reactions. But femtosecond lasers are still pretty novel to our measurements. So I would say there are ways to improve on the ground in terms of measurements. And the computations, like we say, everybody believes experimentalists. Computations, only computationalists believe. So I'm myself a computational guy, so I can be rather critical about my research.
What about just in terms of usefulness? Because there are so many possibilities for different reactions or modeling a collision, different impact parameters. There's just a huge range to compute. Do you find that is it easier just to take an experimental value, or do you actually need all of the detail that you get by modeling a bazillion different cases?
And no, it's not easy just to take experimental data, because experiments are also now heavily relying on theories to extract the needed data. Like in the 70s, you can just run a pure nitrogen flow and easily measure dissociation rate, because it's the first thing that happens in your flow. But what if you need to measure ionic species in the flows? You have to have some kind of model to extract that. And this is actually where the iterations between computations experiments are really helping.
So the models are sufficiently detailed that actually experimental diagnostics are a limitation, being able to
yes
get all the information that you need.
I would say yes. And also you can see the hierarchy, right? I talked about neutral particles for a reason, because neutral particles we studied the most. Now we are going into electrons, plasma, using quantum mechanical methods. So this is we are still not there yet, but we're trying.
So have people talked about using lasers to shoot down hypersonic vehicles by creating plasmas, and so not destroying them, but just messing with their plasma?
Oh yeah, they talk all the time. The problem is that what is called thermoblooming, right? When you want to propagate laser beam through atmosphere, you sort of like start engaging the atmosphere on its own. Even if it's transparent to your wavelengths, if the power is high, right, you start changing the optical properties of the atmosphere, and the atmosphere starts to act as a self-focusing lens for laser beams. So essentially, beam that is flying through atmosphere can collapse on its own, which we don't want to happen. It's called thermoblooming. People, in very recent concept, people trying to use what's called, I forgot what to mention. So essentially, a sequence of focusing and defocusing mechanisms to keep powerful laser propagating through atmosphere. They have the streamer discharge happening in the air, and streamer discharge helps you to actually transmit power without losses. So I'm not sure how it actually works in details, but for DoD purposes, we just assume that you delivered the laser to the surface, like whatever it takes. In the worst case, you can just place laser on the satellite, right, rather than from on the ground. Satellite is easier because there is no atmosphere. And then when you hit the surface, what happens with the surface? And it's actually very rich physics. Like you have very non-equilibrium effects if the surface is dielectric or conductive. No, it's pretty cool physics.
So I also wanted to ask about this shuttle globe phenomenon. So you described a mechanism. Why do you think that mechanism is particularly important? Just naively, I would have guessed that there would be 100 different mechanisms that involve some sort of atomic excitation and emission of light. But what is it? This seems very complicated. You're beginning with oxygen adsorbed on the surface, and then why this particular mechanism?
So your question is why it is important, right? So what happens here is that your surface for the design purposes, right? If you're an engineer, if you want to build a vehicle, you want your surface to as little possible to engage with the flow
Mhm.
Because if your surface is non-catalytic, right, you're maintaining the integrity of the vehicle. When the surface becomes catalytic, meaning it starts to participate in chemical reactions, you don't really want to have that, because you're opening a whole box of worms where you can lose your surface to operation, to all sorts of this mechanism. And you have to be, if you do this, you have to be really conservative how much thermal protection you're designing your vehicle is. So this glow is example that surface is very much catalytic. It encourages chemical reactions, right, with the flow, and you want to have a very good sense how much of this reaction happening. Not even just to see the glow from the orbit or from the ground, but just to see how much energy goes to these excited species in the gas phase and how much remains at the surface, because that will dictate your surface temperature. Just pure design point.
Why do you think that this involves the surface in the first place? I would have thought it, with a shock forming in temperatures of 10 or 20,000
Wavelengths.
K, that there would be enough.
There is no gaseous mechanism provided wavelengths. So wavelengths gives you almost exactly the molecular species that is formed, and you can really track that down. What happens?
Oh, if there are no other questions, thank you, Daniil, again.
You're welcome. So I'm gonna stop here.